back to the deep dive. We're here to take that stack of information you have, all those articles, research, technical docs, and we'll pull it all together into something you can actually use. Today, we're strapping in for a pretty big one. We're looking at the architecture that powers pretty much our entire digital world. We're drawing from some great source material, things like demystifying the digital architecture and some of the core ideas in Foundation and Flight.
Yeah, and this is more than just a tech talk. It's really a systems discussion.
Yeah.
I mean, the sources make a really compelling case that, while almost everyone uses complex software every single day.
Oh, constantly. Ordering food, streaming movies.
Exactly. But most people, they don't really have a conceptual map of how it all works, how it's built, how it scales, and, where the smart part of it actually lives.
Which is a huge gap, right? I mean, if you're a professional trying to get ready for the future, or an educator, or even a student, that gap can make you feel like you're always one step behind. So, our mission for you today is to provide a kind of conceptual shortcut. We want to map out that whole journey, from the very first spark of an idea all the way to a globally scaled AI-powered system. The goal here is that you walk away feeling informed, not just overwhelmed. We're going to break down the blueprint.
Okay, so let's unpack this. Let's trace the start of, any app or digital platform. It never just starts with a line of code. It really begins with getting everyone aligned. The sources are pretty clear that turning an idea into real software needs 4 essential roles to work together perfectly.
That's right. Before anyone even thinks about coding, you have the business function. They're defining the need, the vision.
What are we actually building and for who? Exactly. Then you have design. They're mapping out the whole user experience, making sure it's intuitive, making sure it's something people want to use. Then, of course, development. They're the ones actually writing the code, the logic, and, crucially, testing.
And testing isn't just at the end, right?
No, absolutely not. It's running throughout the entire process to make sure the final system is, reliable and secure.
That structure is so vital because it really dictates how the software itself is organized. When you look at the fundamental architecture, it almost always breaks down into 3 classic layers. You've got the front end, that's the user interface, right? What you're actually looking at on your phone.
Mm-hmm. And then you've got the back end. That's where all the heavy lifting happens.
Yeah.
This is the server-side logic, the processing layer. This is where all the calculations are done, security checks are performed, business rules get enforced. It's the engine room, basically.
The engine room, I like that.
Yeah.
And the third layer, the databases.
Right. The persistent storage layer.
So if the back end is the engine room, the database is what, the fuel tank?
That's a great analogy. It's storing everything from user profiles and purchase histories to all the content that actually makes the application valuable. But they're not isolated. I mean, the real complexity and the really critical part of the architecture is how these layers all talk to each other.
Yeah, that communication link, say, between the front end and the back end, that must be a constant architectural challenge.
It is, you're trying to balance security, performance, latency, all across that boundary. You want the system to feel instant to the user, but you have to securely process requests through the back end, which, requires really fast, really secure channels.
Okay, this is where it gets really interesting for me because now we're shifting from the code, from that software blueprint, to the actual physical infrastructure that hosts it all. Everyone throws around the term the cloud, but if we're going to understand the architecture, we need to know what it really is, and maybe more importantly, why it changed everything.
Well, at its simplest, the cloud is just remote computing resources. Servers, storage, networking, all managed by a provider and accessible over the internet. The Foundation and Flight material draws a really sharp contrast here between local systems or on-premise.
That's where a company buys and maintains all its own hardware in its own data center.
Right, versus cloud systems where they're leveraging platforms from vendors like Amazon or Google or Microsoft.
And the big takeaway from the sources isn't just what the cloud is, it's this concept of elasticity. If I'm running a local system and suddenly get, say, 10 times the traffic I was expecting, I probably crash.
You crash, for sure. But if you're on the cloud, the infrastructure can scale up automatically to handle that peak.
That elasticity has to be crucial for any kind of global scale.
It is. And the basic building blocks that make it possible are always the same. You've got servers running the software logic, databases storing the data, and then the really critical component that links everything together, APIs.
I think we need to go a bit deeper on APIs. In the original script, we just called them messengers, and I feel like that's a bit too simple. What makes a modern API so important architecturally?
Well, APIs, application programming interfaces, they're basically contracts. They define how different pieces of software can talk to each other securely and reliably. They let the front end ask the backend for data, for example, or they let two different microservices exchange information.
So they're more than just messengers.
Much more. Today, most use standards like REST or GraphQL, but their real importance is that they provide a secure, standardized gateway. They manage traffic, they authenticate users, they enforce rate limits. They're like the system's external border control.
So the API isn't just sending a message, it's checking the message format, making sure the sender is allowed to send it and that the system isn't getting overwhelmed. It's a traffic controller.
Precisely. And the vast amount of traffic being controlled is, of course, data. The sources really stress this. Data is the ultimate asset. Its volume, its utility, it drives every single architectural decision.
Which brings us right back to databases and the nuance of choice. We've got SQL and NoSQL. What's the architectural consequence of picking one over the other?
We can break that down. Think of SQL databases. That stands for Structured Query Language as needing structure, rigidity. The consequence of that rigidity is that they can guarantee something called ACD compliance. It's atomicity, consistency, isolation, durability.
And that's vital for things like financial systems, right?
Vital. Anything with high transaction fidelity. Core inventory, banking. If you absolutely have to make sure money is never duplicated and transactions are completely reliable, you choose SQL.
So the architectural payoff for giving up flexibility is total reliability and consistency.
Exactly. NoSQL databases, on the other hand, are all about flexibility. They can handle unstructured documents, graph data, key value pairs, you name it. And the architectural payoff there is just phenomenal speed and elasticity, especially with massive, rapidly changing data sets.
Like what? What's a good example?
Think about personalized recommendation systems, or social media feeds, or real-time data from online gaming. They sacrifice those strict consistency guarantees for just sheer volume and speed.
That distinction, acid versus flexibility, that feels like a core trade-off that professionals really need to get. Okay, so zooming out to the broader system, how do companies actually scale these things globally? What concepts do they use to stay, available and reliable?
The sources really point to three pillars of system performance: scalability, availability, and reliability. And to get all three, modern architecture is heavily focused on something called horizontal scaling.
Okay, let's clarify that. What's the difference between horizontal and vertical scaling?
So vertical scaling is just making your existing server bigger and faster. You add more RAM, a better CPU, but you eventually hit a wall, and if that one big server fails,
Everything stops.
everything stops. Horizontal scaling is different. You add more, smaller, identical servers. This gives you massive elasticity and, maybe more importantly, redundancy. If one server fails, the others just pick up the load immediately. That ensures both availability and reliability.
So when we hear about a company using cloud platforms, they're leveraging global region servers in different parts of the world to get that horizontal scale and redundancy. But doesn't this complexity, adding hundreds of services create a management nightmare?
Oh, it absolutely does. And this is where the concept of microservices comes in, which is a key advanced topic the sources bring up. Instead of building one giant application, monolith companies break their systems into hundreds of smaller, independent services. Each one is managed by its own team, and they all talk to each other using those APIs we mentioned.
And that makes development faster, I assume.
Way faster, but it dramatically increases the operational complexity.
That's a huge trade-off. So you're trading development speed and, I guess, localized failure tolerance for this massive operational headache. To manage that, I'm guessing the way we deploy to servers has also changed. We're not just, logging into a server box anymore.
Not at this scale, no. The software that runs on these cloud servers is almost always packaged using containerization. The big tools here are Docker and management platforms like Kubernetes. This just ensures that an application runs identically everywhere, whether it's on a developer's laptop or across thousands of servers in the cloud. It's really the packaging standard for these massive horizontal architectures.
Okay, so let's recap. Our architecture is now a collection of standardized, horizontally scaled microservices running in containers. They're all talking via these highly controlled APIs and relying on specialized databases. This feels like the perfect segue to the elephant in the room, AI. How does that complex layer fit logically into this whole environment?
Right, we have to make sure you see AI as a data-intensive component. It runs on this exact architecture. It's not some separate piece of magic. The sources are pretty clear about defining AI integration in two main phases. You have training, and then you have deployment.
Okay, tell us about the training phase.
Well, an AI model is only as smart as its data. So the first step is building a data pipeline. Massive volumes of data are pulled from those central databases. They get pre-processed, cleaned, and then fed into a specialized cluster of cloud servers that have huge amounts of computational power, usually GPUs.
So the training requires this immense but temporary burst of resources.
Exactly. The architecture supports the heavy lifting of training the brain, which happens sort of offline, separate from the main user-facing application.
And once that brain is built, the model, how does it get deployed back into the app that the user actually sees?
That's the deployment phase. It's also called inference. The trained model gets packaged up and deployed as just another microservice, another component, often within the backend layer. It's made accessible through a standard API call. So when you ask a chatbot a question, your request goes from the front end, it hits the back end, and the back end just uses an internal API to ask the AI model for an answer.
That really does demystify it. AI is basically a very specialized, very data-hungry piece of logic running on the exact same cloud infrastructure we've just been talking about. And we see this play out in the examples from our sources, chatbots instantly handling customer service requests.
Highly optimized recommendation systems that are analyzing all that NoSQL data to suggest what you should buy next.
And even sophisticated automation processes that are handling complex business logistics like inventory management.
In every one of those examples, the AI component is just an advanced processing layer. It uses the application to communicate and the database to learn and ultimately deliver smarter results.
Okay, so we've covered the idea, the code layers, the cloud infrastructure that gives us scale, and how AI slots in as this intelligent component. Now for the final and maybe most important piece. What does all this understanding mean for you and your career? How does applying this kind of systems knowledge prepare the future workforce?
This is the necessary pivot that the sources really highlight. The traditional value of just memorizing facts is diminishing so rapidly. If systems are constantly adapting with microservices and cloud updates, the premium is now squarely on problem-solving skills that go beyond any one specific tool.
So it's not about being the best at using one particular piece of software. It's about understanding the whole machine.
That's it, exactly. The crucial skill is understanding systems, and you connect the business need all the way down to the data architecture. Can you spot why a system is failing to scale horizontally? When you grasp the architecture, the why and the how, you can adapt to the next new technology, whether it's a new database or a whole new framework.
And the sources didn't just leave this as a high-level goal. They actually provided specific, tangible skills. They mentioned proficiency in Python, which makes sense. It's versatile across data science, AI, backend, strong data thinking. So being able to analyze information and pull out insights, which is critical for feeding those AI models. And finally, a clear understanding of business processes.
That last one is so critical. If you understand the flow of business value, you can make sure that this highly complex, scaled architecture you're building actually solves the real organizational goal. The person who can bridge that gap from the technical blueprint to the business outcome, that person will always, always be invaluable.
That ties it all together perfectly. It links that initial business role from the very beginning right through to the final system and the skills you need. We've synthesized the entire chain. The roles, the code layers, the move to cloud infrastructure, the need for horizontal scale, and then integrating AI as a powerful data-dependent component.
The final thought I want to leave you with, and this builds directly on the educational focus of our sources, is this. The necessary shift has to be away from teaching discrete tools and towards teaching how systems think, how they fail, how they scale, how their different pieces interact. If you can master that process, you're prepared for any digital future that's coming.
A truly provocative thought for us to mull over. We hope you feel you have that shortcut now, that deep dive into the engine that's powering your digital life. Thank you so much for supplying the incredibly rich source material for this analysis. We'll catch you on the next deep dive.